Okay, so now it's recording to the cloud. So good. So that's recording. All right, now we're talking about Teams. So we're talking about this, and then of course, because you put it in the wrong one. We need to go back again. Where did you put it? Post-class addenda. All right. So just so you know, I post the lectures, I post the lecture note, and I post videos of the lectures on here. And then this was a question that Anoop asked about second quantization, about he read in some book that they put you just say, well, here's a minus sign, and this is how you define annihilation equation operators for fermions. And I said, no, that's terrible. There's no physics in that. And so then I explained. I love iPads. I just think we should buy more stock in Apple. So I gave a long answer to make the connection between what the annihilation equation operators do and what wave functions do, and then I gave you at least two or three different ways to understand how the thing goes, and then I wrote it out and scanned it in like this, and so you can see that the connection between what the algebra is doing, the mathematics, and the physics of taking a bunch of things and getting around. We're not going to get to do it in this quarter's course. I'm not putting in things like second quantization, as a fractional quantum effect, or fictitious forces that come from particle statistics or anyons or Chern-Simons theory or anything like that. But understanding the connection with the geometry of how these things move is really important to understanding what gauge fields do, what flux is doing, and things like this. And it also is connected to what happens in statistical stochastic processes. So anyway, so it's all on here. So Mustafa, I hope you can get access to Teams. If you're not, then come to my office and I can help you. Okay, so what I'm going to do today, I've hit the record button. What we're going to talk about is the static susceptibility, which some of you do not know what it is. And we're going to talk about static susceptibility for the ON model for continuous symmetries, Goldstone modes, and the onset of rigidity. So this is a really important lecture for the course. This is the first time that we will really talk about rigidity, which we've not really talked about in either last quarter's course or in the previous weeks, in the previous 2 weeks of this course. I'm going to start off by going over what we did last time, because last time I did it deliberately fast to get it all down so you can see the idea. Now I want to recap it so that you get to refresh it and see what we were really doing. So what we did, what was our goal of our last lecture? We know how to do mean field theory. It's just simply solving a quadratic equation. So we've understood that. What we wanted to do was now look at the effect of fluctuations. When you're doing mean field theory, what you are saying is that the system has minimized the free energy, or in our case, the coarse-grained free energy of the system, what we call the effective Hamiltonian, that describes long wavelength degrees of freedom. In equilibrium, the system is a uniform state. It's spatially constant, and we worked out what that is. And I'll show you that in a second. And now what we wanted to know is, well, in real life, the system is in thermal equilibrium. It's a non-zero temperature. So the system is not all just sitting there, everything in one ground state. Everything is fluctuating. And so we want to now look at what the effect of those thermal fluctuations are, which translate into spatial variations. So what we did was we said, we're going to look at fluctuations about mean field theory, assuming those things are weak. Weak means the lowest order spatial fluctuations about the mean field theory solution, and the mean field theory solution is spatially uniform. Okay, so what was the basic idea? The basic idea was mean field theory is a constant. If I take its Fourier transform, it has no Fourier component other than the zeroth one. That's a constant function. So if I have got spatial fluctuations, then it has non-zero, it has Fourier components for wave numbers non-zero, k non-zero, and that's what makes the fluctuations different from the mean field theory. So what we're going to essentially do is expand in Fourier components. And because we're looking at small fluctuations, what we're going to do is expand in the fluctuations. So there's two things that are small. One is I look at the average value, the mean field value, and now I look at the order parameter at a point in space and see how different it is from the average. Okay, that's the fluctuation in space. Okay, we're going to assume that those fluctuations are small. So we can do a quadratic expansion of the free energy. The other thing that we're going to assume is small, because that's how we constructed the free energy in the first place, is that the system, we're only describing long wavelength fluctuations. We've coarse-grained the system. We don't care about what happens at smallest scales. We want to average those out and just focus on what's important, which is what's happening at long distances. So the way we did this was we wrote down our Landau free energy, which is a free energy where we expand in the gradient of the order parameter. So this is where we're taking a long wavelength approximation. And then we make the small order parameter approximation by saying that this free energy as a function of the order parameter, this uniform free energy, is just a quadratic and a quartic term. These are determined by symmetry, and then in principle they can be a coupling to an external field. And this term here, field T is T minus Tc over Tc, and we in the first week or so of the class we derived this phenomenologically. Okay, now if T is greater than Tc, little t is positive. So what happens is when I take I calculate the solution of the system, so I minimize the free energy. So I have dl by d eta is equal to 0. Then I find that eta is itself equal to 0. So that means above Tc there is no order. That's why we call this thing an order parameter. So the fluctuation then is just eta at r minus 0. So that's just eta of r. If I now take the Fourier transform of this, so you expand f is quadratic and quartic. We're going to do this to lowest order. So we're going to throw away the quartic term. Then we just have grad eta squared and eta squared times its coefficient. So if I now take the Fourier transform of that, what you get is the sum over k of the Fourier transform of eta, k squared absolute value, times a number, which is 2at plus gamma k squared. So this is just, if you like, if you have a quadratic function by Parsifal's theorem, it's going to be diagonal in k space, so that's what you get. I've added here the 0 of energy, which was the coefficient A0 in the way that we derived the Landau free energy. Usually we omit it. I just put it in here just for completeness. One of the things that came up last time, I put a prime on this summation here. Why? Because the order parameter is real in this particular system. So that means its Fourier transform, the complex conjugate of eta of k, is equal to eta of minus k. So all you do is you say eta of r is equal to eta of r complex conjugate, then take it right down its expression as a Fourier transform, and this equation drops out. And so we restrict ourselves to the half plane in k, so maybe kz is greater than 0 would be one way to avoid it. The free energy of the system, eta minus beta f, is then this half integral, functional integral. All that means is we take the product of the Fourier components and integrate eta minus beta f. That's what we get from statistical mechanics. And then I did this calculation for you in class, and what you get is this formula here. Okay, so that was the result of the calculation. And everything here is a Gaussian integral, so it's easy to do this calculation, and it's exact an approximation. So that's the computation of the free energy. So if I want to compute for example, the heat capacity or any other thing, I can just take the free energy and differentiate this and get formulae for it. And if I want to work out how does the heat capacity diverge at the transition, how does the order parameter behave, all of that is in this formula here. Then I showed you we can also calculate for free, without doing any thinking, spatial correlation. So how did we do that? Well, we said that L is quadratic in the order parameter. And we know that if I have a free energy or a Hamiltonian or effective Hamiltonian, which is quadratic in a degree of freedom, and this one it's quadratic in the real part of eta and the imaginary part of eta. So if it's quadratic, then the equipartition theorem of energy says the average energy of that mode is a half kT. And we've got two of those modes, one for the real part, one for the imaginary part. So I know that this thing This is the energy term in here, has expectation value KT. And so then I can read off that the expectation value of the magnitude of eta k squared is just this function here, it's just this over that. Okay, then, so that's fine. So you can say, well, that's nice, but what is the physical interpretation of this? Well, this thing is just the Fourier transform of the correlation function in real space. So here's the correlation function in real space. I take eta, or in general, I would take delta eta of r and delta eta of r prime. I take its Fourier transform, that thing equals this. And you can just check this by doing the Fourier transform. There's the factor of v that comes up here because this integral here does not depend on what r prime is. So if I set r prime equal to 0, cross r prime out here, do this integral, I'll get a number that doesn't depend on what r prime value is. Now when I do the integral over r prime, I'll just get a factor of v. And so I get v times the Fourier transform g hat of the correlation function, and that's this thing here. Now what is the correlation function? Well, we talked about this. So suppose I've got 2 points in space, r and r prime. If eta at r is uncorrelated with eta at r prime, then what that means is if I compute expectation of eta of r prime, by definition of being uncorrelated, what that means is that this is expectation of eta of r prime, and the average of eta of r is 0 because we're in the phase above TC, and so this will be 0. If you are in the phase below TC, you'll do this in the homework, okay, which I will send later, but it's the same thing. So this quantity is 0 if things are uncorrelated. If they are correlated, then it will be non-zero. So measuring this thing is a way to measure, to see correlations in the system. Okay, now here's the other thing. If I take this formula that I've got for the Fourier transform of d of k, so the v's just cancel out, and I get g hat of k is kt over 2at plus gamma k squared. So those of you who've come from, say, have done quantum field theory, they'll say, oh, I know what this thing is. This looks like the Baire propagator or Feynman propagator in a simple quantum field theory or in many body theory. That's exactly what it is. And here, and I'm going to write it like this, divide through by gamma, so it has this form like so. So you can see that this thing, this is 1 over k squared. K has dimensions of 1 over length. If it has dimensions 1 over length, then k squared has dimensions 1 over length squared. So this must also have dimensions 1 over length squared. So we're going to call that length psi greater than. It's the correlation length. It depends on reduced temperature, and it has this functional form. So it says that this length psi greater than is gamma over 2at. And as you noticed last time, as Frank noticed, that means that the correlation length diverges as you go to TC, and that, of course, is the famous result that we explored extensively in last quarter's course on emergence of phase transitions. All of the scaling laws of phase transitions occur because of this divergence of the correlation length. Now, why do I call this thing the correlation length? Well, let's look in 3 dimensions. So the correlation function goes like 1 over, apart from the factor kt, 1 over k squared plus this length squared. Now I take the Fourier transform from k space to real space of this. You all learned this on your mother's knee. This is just a Yukawa potential. And so there is the functional form of it, 1 over r e to the minus r over psi. And so what this shows you is that the correlation function in real space decays with distance exponentially over r. And so this is the length scale over which correlations spatially decay. And so the exponential decay over the correlation length is why we call this length scale a correlation. So that is a partial recap of last lecture. Now I want to go on to something new, and then we'll talk about the ON model. So the thing I want to talk about next then is the order parameter susceptibility, which is something that those of you who took the class last quarter will remember. I'm going to go through a calculation that we did last quarter in a completely different way than we did it last time. So let's write down our Landau free energy. Here it is again with the same form. But now we're going to include this external magnetic field, H of eta, like so. So let's have a look at what happens in equilibrium. So in equilibrium, eta is equal to a constant. But let's set H equal to 0. So what we do is we say dl by d eta is equal to 0, well, L is just the volume times f of eta, because if eta is a constant, the gradient terms go away. So I just have to look at the derivative of this f with respect to eta. And so what you get are the solutions. Expectation of eta can either be this or 0. Now, T is changes sign below the critical temperature. So above the critical temperature, this thing is negative. So this would be an imaginary number. That's not acceptable. So the only solution above TC is this one. But when I go below TC, so T is negative, then this solution is allowed. And this solution corresponds to the minimum of the double well potential. Okay, now, what do we mean by susceptibility? Susceptibility means I take the order parameter, its expectation value, and I look at how it changes with external magnetic field. As I take the system, it's sitting there, it's in some state. Now I apply the external magnetic field to it. How does it orient? What you would expect is that the spins, if there's magnetic spins, are going to start pointing in the direction of the external field. Okay, how much? Well, let's go and see. So what we do is we measure that by this thing, and we make this change. We include the external field without changing the temperature. So it's called the isothermal susceptibility. So now what we have to do to calculate this is we're going to compute the extremum of the coarse-grained free energy. So we're going to look at dl by d eta equals 0, but now we're going to include this h term. So if I go ahead and do that, then you can see that what I get is 2at expectation of eta plus 2b expectation of eta cubed is equal to h. Okay, remember I differentiated with respect to eta, so the derivative of this thing just gives you h, and then these things are just 2at eta, and the 4 comes down, I get 2b eta cubed. And so you can see that 2at plus 6b eta cubed is dh by d eta. Well, this dh by d eta is just 1 over the susceptibility. So I can then say, fine, so the susceptibility is just 1 over 2at plus 6b eta squared. So that is what the susceptibility is. That's the general formula for it. Now, if I'm above TC, then the order parameter value is 0. So this term goes away. And then chi t is 1 over 2at. So this is the susceptibility. And what this calculation tells you is that if I'm going close to a critical point, to the transition point, the susceptibility diverges, and it diverges at least in this level of approximation with the exponent 1 over little t is t minus tc over tc, so it diverges with the exponent 1. Okay. And that's the result that we got last quarter using a different method. Okay, so that is what I mean by order parameter susceptibility. Any questions about this? Okay, so this is more or less review. Now this is not review. Now I'm going to tell you that the susceptibility is related to the correlation function. And the reason it's related is this. What does the spatial correlations tell you? Let me move this thing out of the way. What the spatial correlations tell you is how eta of r prime depends on eta of r. So in other words, here I am at r prime. Let's suppose I apply an external magnetic field, but not spatially uniform, just at this point r. That's going to change eta at this point. If it's going to change eta at this point, because the value of the order parameter at r prime is correlated with this, depending on how far away it is, it's also going to affect that. So applying the external field, which is like what you're asking when you're talking about susceptibility, somehow should also be related to correlations. So susceptibility and correlations are related because they both tell you about how changes to a system are made as you apply an external force, either uniformly or at a particular point in space. Now, yes, question.
Do you see that already as rigidity of the state?
No. Because this is true even when the system has no rigidity. Okay, right? So if let's suppose that I'm in the state where there is no order, the system is disordered. Okay. Now I apply a magnetic field. The system is fluctuating; it's disordered. So this spin over here is still correlated with this one. We just calculate what its correlation function is. It decays exponentially, but there is no rigidity. There is a correlation, but there's no rigidity. They're related. We'll see that. but we're in a phase where there is no rigidity, and yet there is still a correlation. And now when I apply an external field here and make this spin point up, that's going to make this spin preferentially point up, because but if it's far away, then it won't. Okay. All right. Okay. So remember rigidity. Remember the experiment that I did at the beginning of the class. Okay, I took an object. Here's an object. I put it on the table. I took out my finger and I pushed this object, and I was able to transmit a force. This is an amazing experiment, totally amazing. You do not know the physics that explains this experiment. You might know about black holes and quantum field theory and neuroscience or whatever, but you do not know why this thing is moving. You'll know by the end of today's lecture if I get that. Okay, so what's happening here is this force is being transmitted for an infinite range. Okay, that's the difference. Okay, so I answer your question, Mr.
Yes, I forgot we were about TC.
Yep. So when you're below TC, though it's still the same thing. Okay, because there is no rigidity in this sense. Okay, all right. So now let's ask the question. Instead of making an external magnetic field just at this point R, let's make an external magnetic field spatially uniform. Okay, there should still be some connection. So let's see what that connection is. So now we're taking the correlation function and now we're going to integrate it over all space. So let's see what that is. That's the integral over space of the correlation function. So remember, correlation function is translation invariant. It depends on two variables. I've just set the other variable equal to 0, but without loss of generality. So that's what it is. Remember that we calculated this object as its Fourier transform. So e to the r has a Fourier transform. So I can write this object in Fourier space, sum over k, 2at plus gamma k squared, e to the I k dot r, and then I have this integral over r here. So that's what this thing is. And now when I do this integral, all I get is the Kronecker delta of k and 0 times v, right? Just as we talked last time about the Kronecker delta. So when I do this integral, I'm integrating over a volume v, so it's not a delta function. This just gives me 1 if k is equal to 0. K is equal to 0, this is just 1, so this just gives you v. If k is not equal to 0, then I've just got an integral of a bunch of sine waves, and so it averages out to 0. So I get this thing over here. So now that means that in this sum over k is to be set equal to 0. So I throw out the k, I get that. And then this v cancels with this v. And so I get k dt over 2at. So that's what this integral is. And you look at this and you say, well, I've seen this before somewhere. Oh yeah, I saw it up here. This is just kt times the susceptibility. So the susceptibility of the system, or thermodynamic susceptibility, is the integral over the system of the two-point correlation function. And that's a result that we derived in a completely different way last quarter, and we call that the static susceptibility summary. Any question about this?
We derived this above TC, but this
same you can do this thing. You can do this thing below TC, and welcome to homework sheet 1. All right. Okay. So if there's no questions, then I'm going to move on from this. So now we're going to talk about the next topic that we're going to talk about is the ON model. And what we're going to do is we're going to generalize everything I've just told you to the ON model. So those of you who just come in, this is your first experience of this course, you have to go to the website and download my lecture notes so you can keep up with where we are. Okay, so I can't really go back and cover everything for you, I'm afraid. All right, so what we're going to be looking at is section 11.1.1 in my normalization group book, and so the goal in this section, our goal is to look at the response of the system, which has ON symmetry. In other words, instead of it being spins that can point up or down, now they're vectors in n-dimensional vector space, and they can point in an arbitrary direction. Conceptually, it's very similar to what I've just shown you, but there are going to be some differences. Okay, one thing I didn't mention for you, I'm not going to go, I'm probably not going to need to do it in the course, but I've shown you that susceptibility and correlations are related. There's another thing. If you go to a condensed matter physics seminar, or you go to a statistical mechanics seminar, or something like this, you'll hear people talk about Green's functions. Okay, why do they talk about Green's functions? Because if I want to know the response of something, I apply a force here, and then I see how the system responds. That's what a Green's function is in the theory of differential equations. In the theory of fields, quantum fields or statistical fields, what a response function is applying a perturbation here and measuring its effect here. That's what the correlation function did. In the course I taught last quarter, I showed you, I believe, and it's certainly in my book, I showed you that the correlation function is actually a Green's function. It satisfies if I take the equation of state that I've written down here and differentiate it, you can show that the correlation function obeys a differential equation, and that differential equation is an equation whose right-hand side is delta of R. It's a Green's function. What I did here is I used a very, very dirty trick, quick and dirty trick, to get this result without having to solve a complicated hypergeometric functions differential equation. Okay, I got you the result with one line of algebra. Okay, so that you should be grateful that I did that. Okay, so everything I'm trying to do is find smart, fast ways to get to the result. Okay, so now what we're going to do is we're going to suppose we're going to see the response which has O symmetry. So we're going to look at that, and what we're going to see is that the tensor structure is rather surprising. And in particular, what we're going to see is that we're going to be able to derive a theorem called Goldstone's theorem, which I already gave you some intuition about when we saw that the system has a continuous symmetry below TC, and then we're going to if we get time to do this today, we will see how this relates to the rigidity. And in the language of solid-state physics, we're going to look at the spin wave stiffness. In the language of superfluids or Bose-Einstein condensates, we're going to look at the helicity modulus, and so we're going to derive all that. Okay, so that's the goal. So now let's roll up our sleeves and do a calculation. So what we're going to do is we're going to apply an external field, and we're going to apply the external field along a direction which I'm going to call n, like that. So h is equal to some magnitude times a unit vector in the n direction. Okay, question for you. In which space is this vector defined?
The n-dimensional ON space.
The ON space. Okay. This is you might in the lab be doing this in physical space, but what matters for what we're doing now is where it is in spin space. So this is in spin space. And so what do we think that's going to do? So this is going to cause the spins. I'm calling them spins, but there could be any degrees of freedom you want. There could be the components of the 18 component order parameter in superfluid helium-3. So the spins or the order parameter will order parallel to n, and so the magnetization that I get is m alpha. It has component, the expectation value of s in the x direction, and that is going to be just m times n alpha. So as before, this alpha is labeling directions, labeling components in order parameter space. Okay, so without loss of generality, I can take this direction to be the if you like, the x direction. So without loss of generality, I'm going to say n hat is 1, 0, 0, 0, and this here has n components, like so. Okay. All right, now I need to define the 2-point correlation function. So I'm going to define it the way that we did it before, but I'm going to define it in a very strange way. I'm going to define it in terms of the tensor directions. So you'll see why that is in a minute. So we're going to define G parallel as a function of K. So that would normally be the order parameter. I called it eta in the review slides. I'm calling it S now. So normally you would say, well, that's just S of K, absolute value squared. That would be the correlation function. And now what I'm going to be looking at is the component of the order parameter in the one direction. It's called G parallel because it's parallel to the H field, and so there's a 1 here. Okay, so that's the important thing. Now I have to look at the transverse component. So then I'm going to say, well, okay, that's only in the longitudinal direction, in the parallel direction. So let's generalize this. I can say S alpha K, S beta K prime. I can construct this object. So I can take the component of the order parameter in the alpha direction, component of the order parameter in the beta direction, and now I'm going to look at K and K prime. There's no reason why K and K prime have to be the same. So I'm going to make a perpendicular variable that looks like this. But I'm going to put in a few things here to multiply this. So the first thing is I'm going to put in a factor of v. The second thing I'm going to put in is the fact that I expect, since the system is rotationally invariant, I would expect that this thing is going to be 0 and this alpha equals beta. And we'll see that that is actually true. So I'm going to just build it into the definition right now. So alpha and beta have to be the same in order for this thing to not be 0. And then we also know that the system is translationally invariant, and translational invariant means that momentum is conserved. So that means that K and K prime, if they are there in a 2-point function, they have to be equal and opposite. So I also have a delta function of K and K prime should be equal to 0. So I'm defining that like this. So that's the tensor structure. And then after that is done, the only thing is going to depend upon K. This then is a scalar quantity, and it tells you about G perpendicular, because here I'm assuming that alpha and beta, those components, are greater than or equal to 2. So I'm not looking in the longitudinal direction, I'm looking in the direction transverse to the direction in which I'm applying the external magnetic field. So this is called transverse, and this is called longitudinal. Okay, so then you might say, well, that's great. So what do we know about these correlation functions? Well, just like we had the static susceptibility sum rule, so there's also some rules for this. So there's a static susceptibility, chi parallel, which I'll define to be G parallel at k equals 0, and chi perpendicular is equal to G hat at 0. Okay, now I want to just make a comment here. Let me just do this as follows. I didn't point this out when I reviewed the static susceptibility sum rule, but I'm going to do it now. So the static susceptibility sum rule says that chi times kbt is equal to the integral over volume of d dr, the 2-point correlation function. That's the thing. So I want you to notice that this is the same thing as writing the integral d dr g of r. Now I'm going to put in a factor of e to the I k dot r. So that gives me something that now will depend on k. This is a Fourier transform. So I have to evaluate this at k equals 0. Go away. I have to evaluate that at k equals 0. And so in other words, that this is equal to the Fourier transform of g evaluated at k equals 0. So that's what I've used up here. Okay. All right. So now we know that. So let's have a look at the susceptibility tensor. So
Clarifying question.
Yep.
So our order parameter field S now
Yes.
is coarse grained and it does not have Fourier components above a length scale lambda.
Yes.
We still have that.
That's correct. This is the same thing that we had a couple of lectures ago when I first drew for you the, let's zoom back a few hundred years. Yeah. So when I drew this, so remember we derived this, we derived the Landau theory.
Okay.
Right. So we're talking exactly about this Landau theory.
Okay. Thank you.
Okay. All right. So okay. So now I want to define susceptibility. So these are two numbers parallel. I'll just define them to be like that. Now we're going to look at what we actually want to measure. Okay. So what do we actually want to measure? Well, we're going to define the susceptibility tensor in the following way. So what we normally would say is that I take the value of the order parameter in the alphath direction, and now I apply an external field to it in the betath direction. And I want to know, how does M alpha change with respect to a change in the field in the betath direction? So this is a generalization of the idea of susceptibility now to a system which has got more components. And this object, remember that M alpha is minus d free energy by d h alpha. So this object, chi alpha beta, is like this, is equal to d2 f, the free energy, by d h alpha dh beta. Okay, now warning here, I may have got minus signs wrong. Okay, so in my book, I defined it with a minus sign, so I'm going to put it in with a minus. I'm going to put the minus in like that. I don't know. In my book, there may be a misprint in my book. Okay, and but that's the idea. Okay, so what is F? F is the free energy per unit volume or per degree of freedom. So what this tells us, chi alpha beta, tells us how the alphath component of the order parameter is changed when I change the betath component of the external field. So that's certainly something that you would do in the lab. And what is free energy? So that is just the free energy that we've written down divided by the volume of the system, or maybe the free energy divided by n. I've got a lattice system. Okay, but here we've got a continuous system, so it's just F over V. All right. So, okay, now here's the thing that's really important. We know that the original system, the ON model, is symmetric under rotations in order parameter space for h equals 0. So what that says is we remember that we derive that there's a symmetry. If I take the system with the free energy with this order parameter pointing into the direction, I make a global rotation of all the degrees of freedom. A global rotation, everything depends equally. Since all the interactions depend on the cosine of the angle between things, nothing changes when I rotate it. So the free energy was symmetric under rotations in n dimensions. So that was why it's called the ON field theory. So what that means is, since the Hamiltonian of the system is ON symmetric, so the energy doesn't change when I make a rotation, then that implies that the free energy cannot depend on the direction of the field. Okay, so my system is rotating invariant. I apply an external field in this direction, I choose a direction, but all those directions are the same for the system because it's rotating symmetric. So therefore, the free energy as a function of the external field can only depend on the magnitude of the field and not its direction. So it can only depend, so in other words, I can say that F is a function of H, not F of H like that. And when I say little h, what I mean is the magnitude of this vector H, and the magnitude of the vector H is this is a vector in the spin space. So I take all the components in the x squared and the y squared and the z squared and all the other n components directions. I sum from alpha equals 1 up to n, and then I take the square root. That's the magnitude of the magnetic field in this space. So that's the thing that we know. Okay. So now let's ask ourselves, well, the susceptibility is the derivative with respect to h alpha and h beta. So all of these derivatives here, we have to take into account now the fact that the system is rotationally symmetric in ON space. So let's do a little bit of calculus. Let's look at what happens when we use the chain rule. So if I look at what is d by dh alpha, well, that is, since everything I'm going to be doing is only depends upon h, the magnitude of h, then that means that this is dh by dh alpha by the chain rule. Okay, and what is h? Well, h is this thing. So now if I differentiate with respect to alpha, so you tell me what alpha is. So I'm going to take the 17th component of the order parameter, set alpha equal to 17, do the derivative. Then if I compute what is dh by dh alpha, it's just the square root of these things squared. So I find the alpha, I choose alpha to be whatever number I want, 17, find the 17th component, differentiate. I'm just going to get h alpha over h. So this gives me h alpha over h times d by dh. Okay, so check this. Okay, all I've done is just differentiate it. Okay. So then, if I then ask, well, what is chi alpha beta? So chi alpha beta, my susceptibility tensor. So that is, I think this is a correct statement the way I've written it. So that is d2 f by dh alpha dh beta. Well, I'm going to put a minus sign in here. I'm consistent with myself. Okay, so if I do that, then the first df by dh beta is already given by this, so I can write this as minus d by dh alpha times h beta over h df by dh. Okay, so what I did was say chi alpha beta is equal to this formula over here. That's d by dh alpha of df by dh beta, dh by df beta, df by dh beta is equal to this, but I should call this beta alpha. You want me to change it so you don't get confused? No, okay, you can all swap. Okay, so then I get this. So now I have to do the chain rule again. Now I'm going to get a bunch of terms. So let's write them out carefully, and Anoop can check to see if I make a mistake. Okay, so the first term, let's just have a look at this. There's a first term. We can see that the h by d alpha acting on h beta. That's going to give us what? Nope.
Oh,
It's going to give us Kronecker delta of alpha beta, right? dx, what is dx by du? What is dx1 by dx2? It's 0. What is dx1 by dx1? 1. Okay, so this is delta alpha beta. So the first term is easy. So we're going to get minus delta alpha beta. And then once I've done that, I've used up this derivative on the h beta. So what I have left is 1 over h df by dh. So that's the first term. Okay, the second term is I'm now going to differentiate this d by dh alpha acting on the 1 over h in here. When it acts on the 1 over h, I'm going to get minus 1 over h squared, and then I'm going to get some chain rule terms. So let's write those down. So what I'm going to get is minus h alpha over times h beta over h squared. Then I've got the 1 over h that came from here. Wait, what? I don't know if I agree with this is correct. There's too many misprints in this book. Who wrote this book? Wait, let me just check this.
Is it a plus?
Well, there is a plus coming, because what I'm going to write next is minus df by dh. So I think that this, I don't know why I've got this h over here. So let's get rid of this. Go away. I think this h here is a misprint. Okay. So
No, I think that's.
Hang on, wait. Let me finish. And then I get minus h alpha h beta over h squared d2 f by dh squared. Okay, did I get this right?
I think that 1 over h was correct.
Yeah. I think that 1 over h was correct too. So let's put that 1 over h back in. Okay, so I get that. Yeah, so there's no misprints. So this book is perfect.
Should give the Nobel to whoever wrote it.
Yeah. Can I have it in writing? Okay, so I think this formula is in fact correct. All right, so against all odds. So let's group the terms together. So then what I get is minus h alpha h beta over h squared d2 f by dh squared, and then minus 1 over h df by dh. Now what I have is delta alpha beta minus h alpha h beta over h squared. Okay, so that is correct. Now remember that h, the vector h, is equal to h times the unit vector n. So what that means is that where I have h alpha h beta, so that is equal to over h squared, that is just going to be n alpha n beta, where that's the unit vector in the direction of the field. And so what I have then is a very interesting result, which is that the susceptibility tensor can be decomposed into two components. It's n alpha times n beta times the parallel component, chi parallel, plus chi perpendicular of h times this projection operator, delta alpha beta minus n alpha n beta, which projects things out into the perpendicular direction. So this here is parallel, this, and then this is perpendicular. This quantity chi parallel we can now read off from our equation. So read off the chi parallel of h. So chi parallel of h is then just minus d2f by dh squared, and chi perpendicular of h, the transverse susceptibility, is equal to minus 1 over h df by dh. Okay, and this is really important because this thing is just m over h. Remember, df by dh is just the magnetization. So this is what chi perpendicular is. So this is a tensor, but apart from the directions in spin space, it just depends on two numbers, chi parallel of h and chi perpendicular of h. It depends on these two numbers, only those two numbers, because the system has this rotational symmetry in spin space. Okay, so let's just summarize this. So then what this says is, if h is parallel to the direction of ordering, then that means I get chi parallel. If h is perpendicular to the direction of ordering, and that gives me chi perpendicular. It tells me how the system responds to so let's put the system is ordered in this direction. I apply a field in this direction. It just makes the field, it just makes these spins be more pointing in this direction. If, on the other hand, the spins are pointing in this direction, and I apply a magnetic field in the orthogonal direction, it's going to do something else. Okay. Now, what it's going to do is what we're about to see. Okay, so that's that. Okay, now what we're going to see is that this has amazingly important consequences. Okay, so let's have a look. So what we're going to talk about now is Goldstone's theorem. So this is section 11.1.2. Now we're going to look at the excitations of the system below TC. So what is the important thing here? When we're above TC, m is equal to 0. Okay, this is 0, so there's no transverse susceptibility. Okay, I apply a magnetic field, the system doesn't give it out. Okay, it's just fluctuating, so we can. Below TC, m is non-zero. So here's the thing. So for t less than TC, the system exhibits spontaneous symmetry breaking, which we know what that phrase really means. I talked about that at length in the past. And there exists long-range order with m being non-zero. So what that says is, if m is non-zero, so there's long-range order when m is non-zero and h equals 0. Okay? So the whole point about long-range order is this: I take the system, I apply an external field, the spins order, I take the external field away, and the spins still stay pointing there. Okay, that's what a magnet is. That's what a superfluid is. That's what a superconductor is. That's what a Higgs field is. Okay, So now what I'm going to do is I'm looking at the susceptibility when m is non-zero and h is equal to 0. When h is equal to 0, this thing goes to infinity. Okay, when m was 0, it would be 0 over 0, and you could differentiate that and say it's 0. So nothing, no big problem. But when m is non-zero and h is equal to 0, chi perpendicular has gone to infinity. Okay, so that's the thing that is astonishing. So this says that chi perpendicular 0 minus 1, this is h equals 0, is equal to 0, or if you like, chi perpendicular has gone to infinity. Now, we talked about the static susceptibility sum rule. So over here, this is where we talked about it, right up here. Okay? We defined the transverse correlation functions, defined in this way, these numbers, and now we know that this thing is going to infinity. So that means this thing is going to infinity too. So what that says is then that from the static susceptibility sum rule, that says that the Fourier component at k equals 0 of the transverse correlation function is equal to 0, which in other words means that wrong way around, with a minus to the inverse, minus 1 is equal to 0. In other words, it's infinitely correlated in the transverse direction. So what this says is so this naively says that chi perpendicular has gone to infinity. So susceptibility says the following: if I take the system and I apply a small field, what does it do to the system? Normally you say, well, just make some small change to the system, makes the magnetization slightly bigger or slightly less. What we've just found then is that below TC, if I apply an external field to the system, it responds infinitely. There's an infinite response to applying an infinitesimal field. I can get an infinite response with just the application of a small field. Now, you might say, oh, I've seen that happen before. Remember that we saw that that chi perpendicular, let's go back to the original, to what we did over here. Remember over here, we worked out that the susceptibility goes like 1 over 2 AT. T is T minus TC over TC, okay? All right, so this chi tells you how much does the magnetization change as I change the external field. Okay? So what this says is that suppose I have T equals TC. I'm right at the critical point. Now this says the chi is infinity. This says the system is infinitely susceptible. Infinitely susceptible means I can make an order 1 change to the magnetization by just applying an infinitesimal field. Okay. What does that mean? What's the physics of that? Okay, so here's an experiment. I'm going to show you an experiment. Okay, here is a pencil, and I'm going to balance it very carefully on its tip, like this. Except I can't do it because I'm not dexterous enough. Okay, but if I was clever enough, I could balance it on its tip like that. Okay, now if an atom came along and bumped into it, a thermal fluctuation bumped into this thing, it would fall over. You all agree? It would fall over because this thing is poised on the edge of instability. Okay? So infinite susceptibility means a thing is right at the edge of being unstable, and then something comes along, it will always respond, and it will respond massively to an infinitesimal perturbation. Even a single atom can make it do that. That's what this formula means. That's what happens at the critical point. All the stuff that we talked about last quarter, for those of you who are here, for that, all of those critical phenomena came from that, which came from the divergence of the correlation. So now what we discovered is something really interesting. We found that we're not at the critical point. We're below TC. Any temperature below TC, I didn't tell you what temperature it was. Any temperature below TC, what we found is that the system is infinitely susceptible. A very small change makes the system move an arbitrarily large amount. Now, in the scalar case, in this case, why does it do this? Well, above TC, the system is just fluctuating, has no order. As I go below TC, the system wants to spontaneously order. The spins all point in the same direction. That's what spontaneous magnetization is. So at TC, the system is poised on the edge of being, instead of being just randomly pointing in random directions, they all point in the same direction. So it's ready to order. Below TC, if I go for T negative, I go below TC, the system will spontaneously order. I don't need a magnetic field to make it order. Above TC, I do need a magnetic field to make it order. At TC, I need an infinitesimal magnetic field to make it order. And that's what's happening here. Well, I'm way below TC. Any arbitrary change in an external field in a transverse direction will make the system respond. So what's happening is, then what this says is an infinitesimal field in the transverse direction will rotate the direction of magnetization by a finite amount. Because it's a finite thing divided by something that is zero, I get something that is infinite. And this makes complete sense because let's go back to our picture. Where are we? There. Go back to this. This is what we talked about 2 lectures ago. Here's the system. Below TC, the free energy, the uniform free energy, which I call V in this picture, has this rotation shape like this. The system is ordering. I'm applying it to the transverse field. The system orders in a radial direction like this. That's the value of S1, this is the vector spin, S1, S2. I apply a field in this transverse direction. It's just going to rotate the spin. And because it costs no energy to move the spin from pointing in this direction to pointing in this direction, I can move it by a finite amount with an infinitesimal field. That's all this means. All this mathematics I just showed you the last half an hour or so is just telling you that very simple fact that we already saw a few lectures ago just from looking at the cartoon pictures. So, yep.
If it's a good time.
If it's quick, yep.
So then H, you're defining still H. Basically, you're cooling the system below TC, but you're using this H to define that direction as you cool below TC, and then when you say now you're setting H to 0, so the system still has that particular directionality, and that's what.
Well, there's two different things here. One is that I first of all get the system ordered.
Exactly.
So in not very good textbooks, they'll say, well, you lower the temperature and the system spontaneously finds a direction. It doesn't actually do that.
Yeah.
Okay? So the way you do it in the lab is you apply an external field, the spins will point in the right direction, then you take the external field away and you say, ha, I've got the system spontaneously ordered in this direction. Okay? Then I now apply an external field. And I take that ordered state, and now what I'm talking about here is the H field that I'm applying to after it has done that. Is that clear?
Yes.
Good. Thank you for the clarification. Okay, so this corresponds to the infinitely degenerate minimum. So this corresponds to the infinite degeneracy of the minima of the Landau free energy or the effective Hamiltonian. So this wouldn't happen if I had a discrete symmetry, because if I had a discrete symmetry, I would by definition have a countable infinite number of states or countable or finite number. So this doesn't happen there. So now let's think about what's happening. So when I have what this says is if I have a system which is called ON, the ON symmetry gets spontaneously broken, there are two kinds of fluctuations. Longitudinal and transverse. So what does the longitudinal one do? Let's put this back up here again. This is a helpful figure to have in our minds. There we go. Longitudinal one is in the direction of the ordering. So you can see this potential here. If I look in the radial direction, it is up, it comes down, and goes up like that. So the longitudinal direction tries to change the magnitude of the spin of the order parameter in the radial direction. That magnitude, if I take a cut from that, looks like this shape here. So what I'm doing is it wants to be here. If I try to change its magnitude, its energy will either go up this way or its energy will go up this way. So a longitudinal fluctuation in the order parameter will cost energy because it will go up like this. A transverse fluctuation in the direction of the order parameter will be in this direction, and that won't cost energy. So the longitudinal fluctuations cost energy.
So if you had a perturbation in some linear combination of them, would you just project onto the radial?
Yeah. Well, you just project these things. Yeah. Yeah, okay.
Yeah.
So let me finish my sentence. Okay. So the longitudinal one costs energy, and it changes the magnitude. The magnitude of our order parameter. The transverse one changes the direction. And costs no energy. What was the trick for getting rid of this thing?
Go click on the pen at the top.
How do I make it? What is this thing? Thanks. Transverse, so it changes direction and costs no energy. Okay, so everything I just told you is true for spatially uniform system. Okay, if you remember, we started off with our Landau free energy, with our gradient of the order parameter squared term. And then I haven't talked to all the K-space and all that stuff. I haven't talked about K-space for the last 20 minutes. What I've been talking about is just as if the order parameter is spatially uniform. Okay, so now let's ask the question: what happens when we allow spatial variations? In the order parameter. Okay, so now what's going to happen is this. That means we have to take into account, we have to look at the effect of this term in the free energy. Okay, we're going to have to include that. And what do we expect going to happen? Let's suppose I have spatial variations of S in the longitudinal direction. Those variations are still going to cost energy. And now let's look at the transverse fluctuations. Okay, if the system is uniform, the system is like this, it's spatially uniform, I can rotate everything spatially uniformly, just like shown over here, and it costs no energy. Suppose now I say that the order parameter is going to change with position. So let's suppose over here, the order parameter is pointing up like this, and now over here, the order parameter is pointing like this. So if I look at the spatial configuration of S, this n component order parameter starts off over here. As I go along, it's rotating like this. So what you can see is going to happen is that when k is equal to 0, and there's no spatial variation, it costs no energy. If I make that it changes direction and it does it over a distance that's, say, from here to the moon, it's going to cost maybe 10 to the minus 20 EV of energy in order to do that. If, on the other hand, I make it rotate over a distance that is only 3 inches, that's going to cost a lot of energy because it's going to have a very high gradient. The gradient is just the distance over which it changes divided by the distance squared. So that means that for k going to 0, this energy cost is going to 0. So what we've just deduced then is that the longer the wavelength of the fluctuation, the smaller is the energy cost. And this is only true for the transverse fluctuations. The longitudinal ones always cost energy. So I'm going to put that there in a different color so you remember that. So what this says is that the system with ON symmetry has an excitation spectrum with modes that have energy going to 0 as k tends to 0. So the excitation spectrum does not have a gap for the transverse modes. No gap for the transverse modes. So just by ordering, having a continuous symmetry, we know that now the system, the excitation spectrum of the system, must look something like this. If I plot k and I plot the energy as a function of k, what we've deduced is that there have to be modes that go to 0 as k goes to 0. Okay, so this is true for the transverse directions. But for the longitudinal directions, the spectrum must look like this. That's the difference. Now, how many of these modes are there? Okay, is there just one mode? How many modes are there like this? So let's think. The difference between these gapless modes and these gapped modes, these are gapped, no gap. The difference between them is whether they're longitudinal or transverse. So there could be more than one transverse mode. How many transverse modes are there? Not you. You answer the question. Not you, you're the grader. Somebody else. Okay, something in the back row. Fred. Nope. I've got n modes. So I've got n degrees of freedom. Okay. So one mode is in the longitudinal direction. Okay, it just goes like this. How many modes are there in this direction? Here n equals 2. There's one mode. It goes around like this, right? Suppose I had a 10 component order parameter. Wouldn't know how to draw it, but it would be the same thing. How many modes would there be in this transverse direction? It's n-1, exactly. There's always one mode that increases the magnitude. Remember, this is an ON symmetric thing. So there's one mode that corresponds to the radial direction, increasing the magnitude of the order. And then there's n-1 modes that go in directions that are transverse to that. So there's these transverse modes. There are n-1 of these. And then there's one of these, and they add them up, there's n modes altogether. And there's n modes because I have an ON model. I've got n degrees of freedom, and so all my modes can be diagonalized, and all the modes of one that's in the two direction, n-1 transverse. So we've deduced something very interesting. We've deduced that there are n-1 low energy modes, and low energy modes have all sorts of interesting effects on the system. These modes have a name, they're called Goldstone modes. Okay, so we're going to finish here. Let's ask ourselves the following question. Examples of Goldstone modes. I want to just see if I have this in my book, or if I'm just going to just make it up. Okay. So Goldstone modes are modes whose energy or dispersion relation, since E is h bar omega, goes to 0. So just give me an example of such a mode. There's one in this room right now. Sound wave. Okay. Sound wave has obeys the wave equation, and its dispersion relation goes to 0 as k goes to 0. The dispersion relation for sound wave is omega equals ck. My question for you: is a sound wave a Goldstone mode? Sure, you know too much. You took it last year.
I had a good.
Is it? So the question is this: sound waves. The wave equation gives that the energy is equal to h bar omega. Omega is equal to c times k. So the question is this a Goldstone mode?
Sound waves.
Okay, yeah, you can answer because you haven't taken this course before.
I guess the two thoughts I'm having, one is that for sound waves, there's no symmetry that we grow. And also I believe pressure waves are longitudinal and they're not transverse. So I'm gonna say that they're not full sound waves.
Okay, so the answer is no. And the reason is because they are longitudinal. So you're right. Okay. There's also suppose I took a liquid and I sheared it. I can make some kind of waves go through the liquid like that. There can be a sound wave, which are longitudinal. There can also be waves like this. Okay, are those waves Goldstone modes?
No, because of the same shear is very small liquids of the transverse.
You're exactly right. Okay? So even if I looked in a liquid, even if I looked at transverse waves, they're also not Goldstone modes because they don't follow from spontaneous symmetry breaking. Okay, right. Now let's talk about a solid. Okay, so I've got a solid. I've got a crystal. Okay, I hit it. Okay, you heard it. I transmitted a sound wave through the solid. Was that sound wave a Goldstone mode? Somebody else? Yeah. Okay. So you're saying no, this is not a goldstone. Okay. Okay, anybody else? Are you? Anybody else? Anybody else? Graduates? Any of the neuroscientists? Goldstone mode, yes or no? Okay, I'll put you out of your misery. The answer is yes and no. Okay, why is it yes and no? Okay, somebody else has an answer. So, Frank, right? Yeah. Hold your horses. Somebody else. Chan. Yes and no. Why? Don't look at my book. Think. Okay.
Does it depend on like the crystallographic direction? Is it
Right.
the phonon is applied to?
Yeah. It would, yeah. You're going in the right direction. Okay. So let's. Anybody else want to add anything before I give the answer away? Okay, Frank, you had your hand up.
Is it something to do with while it's in the like the solid table material versus
No, it's not. It's not that. That's another habit. But it's related to something that somebody said useful. You asked me a question about this. Okay, so when I'm doing this, I'm exciting both longitudinal and transverse modes. Okay, the longitudinal modes are definitely sound waves as well. Okay, but those modes are there in the liquid. They're not Goldstone modes. Okay, the transverse modes, which you can hear as well, those are not there in the liquid. And those are Goldstone modes. Okay, why are they not there in the liquid? Well, if I take the limit as k goes to 0, a liquid cannot support a shear. If I take a liquid and I shear it by a long wavelength thing, it will just flow back into whatever shape it has. It has no static shear modulus. The solid has a static shear modulus. So those transverse modes come from Goldstone modes. Now you said they don't break the symmetry. There's no continuous symmetry. Okay. Now remember when we talked about in the first lecture of the class, I don't know if you were here for that. In the first lecture of the class, we talked about what is a solid. A solid has periodic lattice structure. Right? Okay, that's not true. Okay, a solid sometimes they can have a periodic lattice structure, but the important thing about a solid is, first of all, it has a static shear modulus, and second of all, it has spontaneously broken translational symmetry, because the solid is sitting there and it has a central mass. Not anywhere, like the gases. So the solid, when you form a solid, the solid transition is the spontaneous breaking of translational invariance. So it's the breaking of a space-time symmetry. So that's the Goldstone that it corresponds to. So the solid, I've broken if I have a crystal, and suppose this table is a crystal, which it isn't. Suppose it were a crystal. I've got a continuous symmetry, the atoms can be anywhere I like, and then they sit in periodic lattices, just like you do. You all sit in the same chairs that you've always sat in for a whole quarter, okay? You have spontaneously broken translational symmetry and chosen to sit in those chairs, okay? Nothing made you do it, okay? It's a spontaneous symmetry break. So you've reduced the continuous symmetry, which is space-time Galilean invariance, to a discrete symmetry, which is the lattice symmetry, reciprocal lattice. Okay, so that's where that's where we'll finish for today. Okay, happy? You still don't know how to explain this experiment. I move my phone on the table. So next lecture, we will explain that experiment. Okay, but not today. All right. So let me turn off the recording and